We'll wait for a few minutes for others to join. I hope I am audible. Santosh, can you confirm?
You're audible, sir.
Thank you. All right, so welcome everyone to week 9 tutorial for the course IC engines and gas turbine. So in the previous tutorial, we started with the gas turbine topic where we discuss about the types of gas turbine. The first was the open cycle gas turbine, other was the closed cycle gas turbine, where we also started with the efficiency of the Brayton cycle. We saw the effect of pressure ratio on the work output and the efficiencies. Also, we calculated the maximum work output for the optimum pressure ratios. So let us start with today's tutorial. Let me just share my screen. I hope my screen is visible. Can anyone of you confirm? Is it visible?
No, sir,
Santosh,
it's not.
it's not visible. Okay, just hold on.
Yonda.
Let me again reshare. Share screen. I hope it is visible now.
Yeah,
Is
sir,
it visible?
visible, visible.
Thank you so much. So let us see why I'm not able to connect. Yeah, okay. So we had expression for optimum pressure ratio, R optimum, RP optimum. Okay. So what was the expression? It was T higher to that of T lower to the power of gamma by 2 times gamma minus 1. Okay. Where T higher was the T3 and T lower was the T1 in the cycle. Now we need to prove, question is, prove that maximum pressure ratio RP maximum is equal to optimum pressure ratio square. Okay. Let us see how we can do that. So we have the cycle like this, where we have pressure versus volume, oh sorry, temperature versus entropy. Okay. So we know that the cycle, actual cycle looks like from 1 to 2, 2 to 3, heat addition, 1 to 2 isentropic compression, 2 to 3 heat addition. from the heat exchanger, 3 to 4 heat, yeah, and expansion, and finally it is rejection. Okay, so cycle was 1, 2, 3, and 4. So this is entropy is constant. If I'm saying my pressure to be, sorry, my pressure ratio to be maximum. So what is the condition when pressure ratio can be maximum is when from 1 to 2 I am directly going till 1 to 2 dash. Okay. So from 1 to 2 I'm directly going to 1 to 2 dash. So maximum pressure ratio means maximum pressure after the compression can be reached and maximum temperature it will reach to. That is temperature 3. So this is 2 dash. Okay. So RP maximum will come when it is P2 dash by P1. And from the expression for isentropic process, it is equal to T2 dash by T1 to the power of gamma by gamma minus 1. Okay. And we can see that at this point, T2 dash is equal to T3. Okay. So we can also write this as T3 by T1 to the power of gamma by gamma minus 1. Okay. Gamma by gamma minus 1. All right. So T3 is nothing but the higher temperature of the cycle and T1 is the lower. Again, it is T higher to that of T lower to the power of gamma by gamma minus 1. And if you observe from the expression of the optimum, if you just multiply with 2, so this 2 and 2 cancels and this become exactly the maximum pressure ratio expression, which is square of the optimum pressure ratio. So we can directly write that therefore RP maximum is equal to RP optimum square, and hence it is proved. Any doubts in this? Hence proved. Clear? Any doubts anyone has? Ratish, Tennyson, Santosh, do you have any doubts? Pretty much clear? So by pressure maximum, I saying that I'm after the compression, I'm saying that my pressure in the cycle will be till the maximum value, and it at maximum value, eventually the temperature will also be maximum. So instead of going from 1 to 2, I'm going to 1 to 2 dash. Okay. Can anyone confirm me? Any doubts here or no doubts? So we can proceed. Santosh, any doubts?
No, sir, no doubt.
Okay, all right.
If any doubt, I will ask in
Yes.
between the class, sir.
Okay. So now we will see one plot for work net versus pressure ratio. So work net versus pressure ratio. Let us see. So work net versus RP. So we know that efficiency is nothing but 1 minus 1 by RP to the power of gamma by gamma minus 1. We have derived this expression. When I say that an efficiency is nothing but equal to work net by heat added. Okay. So when I say that when my RP is equal to 1, when RP is equal to 1, we know that efficiency will be 0. This implies my work net will be 0. Okay. So I can say that if I start from value 1 of RP, okay, if I say I start from value 1, so my eventually the work net will also be 0 at this position. Then I'll draw one plot. Okay, let me draw it once again. Now the question arises, this will be, as we have calculated the optimum pressure ratio and work we get for the optimum pressure ratio, we get the maximum work output for that. We have derived this thing in the previous tutorial. So when I say, suppose my R optimum, RP optimum is this. So at that point, I will be getting maximum work. Okay, maximum work. It is not at the midpoint. RP is never at the midpoint of the this, if you can say, in a parabolic shape form. Okay, and if I say my RP maximum condition, when my RP is maximum, when, let me write it another color, when my RP is maximum, we have derived this expression RP maximum is twice of, is the square of RP optimum. But when I'm saying my RP is maximum, that means my cycle is not providing any work, because we are going from 1 to 2 and there is no other process which will make the cycle to get completed. Okay, because we have eventually reached to the maximum temperature. So there won't be any heat exchange which will happen from the heat exchanger. So here we are not getting area of the graph. That means eventually our work output will be 0. And if work output is 0, this implies my work output is 0, work net is 0. That means my efficiency will also be 0. Okay, for that cycle. Okay. So I can say directly as in terms of work output, if I say my work output is 0. So again, this will be the position where my RP will be maximum and work will be, net work will be 0 again. Now the question arises, we have two areas here. So area 1, this is area 1 and this is area 2. Why I made area 1 to be lesser compared to area 2? Because we have just derived this expression that maximum RP is square of RP optimum. So eventually if I say my optimum is 2, suppose, let us take an example. So maximum will be 4. So it won't be in the middle. The optimum will not be in the middle, and the area of the maximum region, that is the second region, will always be greater than the area of the first region. Okay, if I take RP optimum as 3, then maximum will always be 9. Okay, so from 1 to 3, the distance is 2. Let me write again. If I'm saying if my RP optimum is 3, then my RP maximum will be 9. So from 3 to 1, the difference will be 2. And from 9 to 3, the difference will be 6. So eventually the shift is larger. And if shift is larger, the area covered by the second region will also be larger. Okay. It won't be any time in the middle. Okay. I hope this is clear. So we can say that since RP maximum is square of RP optimum just derived above, therefore region 2, like this, area of region 2 will be greater than area of region 1. Okay. All right. I hope this is clear. Now let us come to the concept of isentropic efficiency of compression and the turbine in the cycle. Isentropic efficiency of compressor and turbine. So isentropic of efficiency of a compressor is nothing but isentropic efficiency of a compressor is defined as a ratio of idle enthalpy rise to that of actual enthalpy rise. So efficiencies can never be greater than 100 or equal to 100. If sum of can be equal to 100 in an ideal scenario, which is not realistic. But efficiency of a system can never be greater than 100 for any cycle in the real world. Okay. So if it's so, then it will lead to discovery of perpetual machines as well. Okay. To that of actual enthalpy rise. Okay. And what is isentropic efficiency of a turbine? It is defined as the ratio of actual enthalpy drop to that of ideal enthalpy drop. Okay. Let us see from the plot. Let me make the cycle, the Brayton cycle plot once again. Then you will understand in a much clearer way. Okay. So we have temperature entropy plot. Okay. Let's make the process once again. 1 to 2, 2 to 3, 3 to 4, and 4 to 1. 1, 2, 3, 4. Okay. Compression, heat addition, expansion, or the work by the turbine, and heat rejection, because it's a closed cycle gas turbine. So what I'm saying, for an isentropic efficiency of a compressor, it is basically the ratio of ideal enthalpy rise to that of actual enthalpy rise. Okay. So what do I mean by ideal enthalpy rise? That ideally enthalpy should go from 1 to 2. But entropy, always remember that from the first law of thermodynamics and second law of thermodynamics, that entropy of a system can never be less than 0. Never be entropy of a system can be equal to 0 or greater than 0. Okay. But entropy of a universe is always remains to be constant. That is system plus around. Okay. So, and greater than 0 as well. So entropy is never going to be less than 0. So internal entropy generation, let me write ds of a system is nothing but S generation plus net heat interaction from the surrounding. Okay. So if suppose I have a system, let me give you a basics of this thermo entropy part. Okay. So one can be the system itself has its internal irreversibilities, or it can have interaction from heat interaction from the surrounding if it is an open system. Okay. So, or even a closed system. So heat interactions can be possible. So because of the internal irreversibilities IIR, and other is the heat interaction. So this is the heat interaction. This is the internal irreversibilities. The entropy of a system is defined with the sum of these two. Let us take an example, a basic example. Suppose you are preparing for an exam. Okay. Either you will think that you are preparing for an exam, or you won't think at all. It won't be something that something negative will happen, that you will go in a vacuum side. Okay. Towards the negative side, the thought process. So either I can say my thinking, so this is basically my thinking is related to the S generation. So S generation, either I can think or I cannot think. Either it will be equal to 0 or greater than 0. And if whatever I have thought, 0 or greater than 0, the other way is I can prepare for the exam. So it can be equal to 0, less than 0, greater than 0 as well. Okay. So this is just a glimpse of this I want to give for the entropy generation. So entropy is always going to increase. So in actual scenario, when the fluid transferred from 1 to 2, it was an ideal scenario. Okay, that entropy was remaining constant. But in actual scenario, the entropy won't remain constant at all. Okay, entropy won't remain constant at all. entropy is going to increase for the system. Either you are going to think or you are not going to think. Irrespectively, you are taking in adiabatic scenarios. Isentropic scenario is nothing but reversible adiabatic. So when I'm saying my ds of a system is equal to S generation plus dq by t, even if I'm saying I'm taking an adiabatic scenario where heat exchange is zero. So either I'm going to think or either I'm not going to think in a basic sense. Either there will be a reversibility or not. So no internal reversibility will only come in an ideal scenario when you are going from 1 to 2. That your entropy is going to remain same. That is your S1 is equal to S2. But in actual scenario, the entropy is going to eventually increase, okay, of the system because of the presence of lot of molecular disturbances, okay, at the molecular scale level. So your entropy will always be, so if entropy is going to increase, eventually the enthalpy rise is also going to increase, okay, enthalpy rise is also going to increase. So I can write isentropic efficiency of a compressor is nothing but H2 dash minus H1 to that is your realistic scenario to that of H2 minus H1. That is your ideal scenario. That is isentropic scenario. Again, isentropic means internally reversible plus adiabatic. So adiabatically, I am saying if it is internally reversible, then it's going to be zero. If it is not internally reversible, it is going to be greater than zero. Okay. So in actual scenarios, S generation will always be greater than zero. Okay. Let me write adiabatic. Okay. So that is H2. Sorry, I am my bad. It is always less than one. Less than one. So it will be actual ideal by actual. So actual value will be always higher. So what I have written defined as the ratio of ideal to that of actual. So ideal is H2 minus H1 and actual is H2 dash minus H1. Yeah. Lower to higher. Efficiency is always lower to higher. That is why it's going to come to be less than 1. And enthalpy can be written as Cp times T2 minus T1 to that of Cp times T2 dash minus T1. If Cp is going to remain constant, so in terms of temperature, it will be T2 minus T1 to that of T2 dash minus T1. So this is your isentropic efficiency of a compressor. Isentropic efficiency of a compressor. Similarly, if I'm saying isentropic efficiency of a turbine, so it will be ratio of actual enthalpy drop to that of ideal enthalpy drop. What do I mean? So actually I was going in actual sense I was going from 3 to 4 where my entropy was constant. Okay? That is your S3 was equal to S4. This was an idealistic scenario, but it won't be idealistic always. Let me make it a straight line. Okay. And ideally, you are not going to get the maximum work output directly from the turbine in ideal scenarios. There will be some losses. So eventually there will be some losses and entropy rise will be higher. So that means effectively my entropy is going to increase again. So my entropy will be not from 3 to 4, but from 3 to 4 dash. From 3 to 4. So it will be actual enthalpy drop to that of ideal enthalpy drop. Actual to ideal. Okay. So let me write. Actual is S3 minus H4 dash to that of S3 minus H4. And again, in terms of temperature, it will be T3 minus T4 dash to that of T3 minus T4. This cancels out, and you are finally left with isentropic efficiency of a turbine is nothing but T3 minus T4 dash to that of T3 minus T4. And this is your expression for isentropic efficiency. Okay. So again, I'm saying isentropic basically means, if anyone of you is still confused, isentropic means reversible plus adiabatic. Okay. reversible plus adiabatic. Let me move this to here as a shortcut. All right, I think this will be fine. Now let's do one numerical related to this. Air enters the compressor at a pressure of 1 bar and at a temperature of 27 degrees Celsius, operating on Brayton cycle, having the pressure ratio equal to 6. Then find the cycle efficiency and maximum temperature of cycle if I am given that work done by turbine is 2.5 times of work done by compressor. Please do this question. Take few minutes, understand the question, very simple question, and solve the numerical. And meanwhile, if anyone has doubt, you can ask. If anyone has done, please tell me the answer, the efficiency and the maximum temperature. Okay, anyone got the answer? Tennyson? Did you got the answer? Yes, no. Pratish, Santosh, Santosh, did you got the answer? Hello, am I audible? Can anyone confirm me that I'm audible or not?
Audible, audible.
Okay. So did you got the answer?
Just doing working with it.
Okay. Okay, let us see the solution for it. Maybe you can verify your solutions as well. So we are given that air enters the compressor and pressure P1 is given and temperature T1 is given from the cycle. So P1 is given to be 1 bar and temperature T1 is given as 27 degrees Celsius, that is 300 Kelvin. 27 plus 273. And pressure ratio is given as 6. RP is given as 6. Okay. And it is said that work done by the turbine is 2.5 times of work done by compressor. Okay. So if I am given the pressure ratio to be 6, so pressure ratio is nothing but T2 by, oh, sorry, not T. So T2 by T1 is given as RP to the power of gamma minus 1 by gamma. Okay. So you know what is T1 is 300, RP is given as 6, and air is entering. So air has a adiabatic index as 1.4. So it will be 0.4 that of 1.4. It comes out to be 500.55 Kelvin. Okay. So temperature T2 is this. Okay. This is a temperature T2. Now we need to get the temperature T3. From where we will get from the expression work done by turbine. So work done by turbine is nothing but H3 minus H4 is equal to 2.5 times of H2 minus H1. Okay. H2 minus H1. So in terms of Cp, we can write T3 minus T4. Cp cancels out. So T3 minus T4 is equal to 2.5 times T2 minus T1. So we can put T2 and T1 here. 2.5, T2 is 500.55 and T1 is 300 Kelvin. So from here, T3 minus T4 will come out to be 501.37. Still we don't have T4. How we will get the T4? So either we can get T3 in terms of T4. One way is this. So we know that P2 by P1 is nothing but P3 by P1 P4. Okay. P2 by P1 is equal to P3 by P4 to the power of gamma minus 1 by gamma is equal to T3 by T4. What do I mean to say that? This can be written P3 by P4 is equal to T3 by T4 is equal to P3 by P4 power gamma minus 1 by gamma. Okay. So P3 by P4 is again nothing but your what? It will be your pressure ratio, in terms of pressure ratio. Okay, so from here again you can write why am I T3 is nothing but 1.66 times of T4, and you can put this T3 here. After putting this T3, 1.66 times T4 minus T4, you get 501.37. So from here, your temperature 4 will come out to be 759.65 Kelvin. And therefore, T3 will come out to be 1.66 times of 759.65, which is equivalent to 1251.03 Kelvin. And this was asked, the maximum temperature. This was asked from you. Okay. Now you got the maximum temperature. Also efficiency. Efficiency we know directly. 1 minus 1 by Rp to the power of gamma minus 1 by gamma. So 1 minus 1 by Rp was 6. Gamma minus 1 is 0.4 by 1.4. This was easy to calculate. So it is 40.06%. Answer. All right. Clear? Any doubts? Anyone has at any step? The trick was in getting the T3, not the efficiency. Okay, if there is no doubt, we can proceed further then. Now we need to deal with. So we have one gas turbine, that is an ideal gas turbine, that is your Brayton cycle. Now we need to improve that gas turbine. What are the different ways? Let us see. Let me write that. Methods of improving performance of gas turbine. We know that efficiency is nothing but net work by net heat supplied. Efficiency is nothing but work net to that of Q supplied. And work net is nothing but work by turbine minus work by compressor, because turbine is a work producing device and compressor is a work accepting device due to that of Q supply. So efficiency can be increased when either you increase the work by the turbine, either you decrease the work by the compressor, or you decrease the heat supplied. Okay, there are three different ways. The first way will be decreasing the heat supply. Let us say this way is number one. Number two will be either you increase the turbine work output, and third will be when you decrease the compressor work output. Let us deal with the case number one. Okay, case one. That is regeneration in the gas turbine. Gas turbine GT. Okay, so what do I mean? I'm reducing the heat supply. So I'm not burning more amount of coal or fuel, whatever I'm using in the heat exchanger. Instead of that, I'm using the exhaust of the turbine, which is coming from the output of the turbine, that is the temperature from fourth, and using that high temperature to heat the incoming fluid temperature before the compression process, before the before the heat exchanger process, after the compression process and before the heat exchanger process. So let me write, it is a process. It is a process in which turbine exhaust are utilized to increase temperature of compressed air before entering the combustion chamber. Combustion chamber. Let me denote combustion chamber by CC. All right. So what I'm doing basically, I'll make the cycle so that you guys understand a schematic diagram first. I have first was this is compressor. So the air enters here. That is stage one. Then it goes stage two after the compressor. Now before entering the combustion chamber, so this is your combustion chamber. Okay, I'm using the heat exchanger. How? Let us see this. Combustion chamber. Then it goes to turbine. Turbine. And output of this turbine, instead of going directly to one, it's going basically here. Okay. So what is basically happening? This is 1, 2, 3, and output of the turbine is 4. And there is a heat exchanger directly. So this fourth temperature, regenerator basically, heat exchanger is nothing but your regenerator. Where the temperature of fourth, this was fourth, and after that you are getting some temperature B, let us suppose. And before entering the regenerator, temperature was 2, and after regenerator it is A. Okay, and before the combustion chamber also. So before combustion chamber and after the compression, the temperature rise was from T2 to TA, and then it was entered into the combustion chamber. Then eventually, if your temperature is already high, so your amount of heat supplied will be less here. Okay, amount of heat supplied will be less. So keep in mind here that temperature of 4 will always be greater than temperature of 2. Then only it will happen. So let us see the cyclic process of it. Just take a minute and absorb like what I have made here. Okay. First, you need to absorb the diagram. The air entered through 1 into the compressor. It get compressed. It reached temperature T2. Before entering the combustion chamber, it was passed through a regenerator where it took the heat from the exhaust of the turbine, that is and reached a temperature A, and then it entered through the combustion chamber. After the combustion chamber, the temperature was T3 and it entered to the turbine. After the turbine, the exhaust was at T4, and that fourth temperature is entered into the heat regenerator once again, which gave the heat from this to uh, the output of the compressor. It reached the temperature. Okay, reached the temperature. All right. I hope this is clear. Now let us draw the plot for it also. Okay. Temperature, entropy. So we say that from 1 to 2, it was a compression process, 1 to 2. Then from 2 to point A, the temperature will rise till the heat exchanger, regenerator, that is A. And from A to 3, the temperature will rise further because of the combustion chamber, that is 3. And then from then it will pass through the turbine to produce the work. Let us say it reach the temperature B somewhere. I should not make here, otherwise my diagram will be much bigger. Let me directly make this and this to be a point. Okay. Then it pass through a process that is 4 through the turbine. Okay, and we have to keep in mind that temperature of the turbine output, that is T4, is always greater than T2. I have written that this point here. Okay, keep it in mind. And then it further rejected the heat till 2. Okay, but on the cause that it provided, the exhaust of the turbine was passed through the regenerator, and eventually the output of that was B. Okay, was B. All right. So let me make the points here. Point A will be this temperature TA. The B temperature will be this TB, and this is T4, and this is T2. Okay. So we have marked all the temperatures here. T2, TA, TB, T4. So from process this till this, from process T2 to TA, this is a regenerator. And from 2 to 3, remaining 2 to 3, sorry, A to 3, it will be combustion chamber. Okay, it will be combustion chamber. I hope this much is clear. Okay. Let me write some terminologies here, which I will explain later. So the cyclic process goes from this. The few terminologies I'm writing here. The first one is TMR. So it stands for mean temperature of heat rejection. Other is TMA. It is mean temperature of heat addition. And the other is SFC. It is specific fuel consumption, as we saw in the IC engines as well. Brake specific fuel consumptions. Specific fuel consumption. These are some 3 terminologies. Now the question might arise, how we will get the temperature A and temperature B. So far we were getting temperature 1, 2, 3, 4 in the cycle, but we have not introduced any regeneration by that time. The question can come, how to get the temperatures. So one way is that just you're exchanging the heat. So whatever heat was given by the exhaust was taken by the exit of the compressor. So what do I mean by that? H of A minus H of 2. So from 2 to 8, 2 to A, that was your the process till which regeneration was happening. So H of A minus H of 2 is basically H of 4 minus H of B. Okay. This was the exhaust. This was the exit of the compressor. So whatever heat exchange was happened from the exhaust, it was taken by the exit of the compressor. Okay. And in terms of, you can write CP. So this is CP. Suppose I'm saying that exhaust gas is a mixture of multiple gases, not only the clean air. If exhaust gas comprises of nitrous oxides and some another elements as well, then that will be a CP of a gas, whereas in the entry of the compressor, it will be a CP of a air. Okay. So let us say if CP of air is not equal to CP of gas. So here it will be Cp of air times Ta minus T2 entry of the compressor Generally, it will be same, but if it is given that exhaust gases of different, then the CP will eventually change, and they will give the examiner will give the CP to you. And this was H4 minus H3, H4 minus HB. So it will be CP of a gas times T4 minus TB, T4 minus TB. Okay. I hope this is clear. Cp of air into Ta minus T2. So by this heat exchange, so one of the temperature rise you will be knowing that either Ta or Tb, and from there you can get the other temperature. Now let us draw a comparison table to understand how we have improved the efficiency and what other terms we have introduced, these three terms which we have introduced, and how they will be effective. Okay, let me draw a table. Till here, anyone has any doubts? If you have doubts, please ask.
No, sir. No.
Okay. So if the cycle didn't add regeneration, it would have directly gone from 1, 2, 3, 4, 1. That would have been the process. But now the regeneration has been added, so it went from 1 to 2, 2 to A to 3, 3 to 4, 4 to B, and B to 1. Okay. So let me write a comparison table. That is 1, 2, 3, 4, 1. That is your without regeneration. And another is 1, 2, A, 3, 4, B, 1. That is with regeneration. Okay. So let us write the point by point. Earlier, the work by the compressor was H2 minus H1. Enthalpy change from 2 to 1. Okay. This will again be same for regeneration as well. It is same H2 minus H1 because compression is going from 1 to 2. Next is work done by the turbine. So turbine is going from H3 minus H4. Similarly, it will also be same. Work done by turbine will be H3 minus H4. There is no change in work done by compressor and turbines. So eventually, if there is no change in the work done for both of them, so work net will also be same. Work net will be work turbine minus work of compressor, which is again same. Work net is equal to work turbine minus work of compressor. Same. Now the change happens to the heat supplied. What will be the change? So earlier the heat supplied without heat generation was H3 minus H2. So from 3 to 2, the heat generation was there earlier. But now the heat supplied was there. Now heat supplied will be from 3 to A. So less amount of heat is added. So Q supplied is S3 minus H. S3 minus H. This is a difference. S3 minus H. All right. So eventually you have reduced the heat supply. So efficiency is going to increase. So earlier efficiency without was work net by QS, but here the efficiency will be work net by QS. And you have reduced the heat supplied, so eventually your efficiency has increased. Okay. Now what will happen to the terminology, that is mean temperature of heat addition and mean temperature of heat rejection. So earlier you are providing, let us deal with mean temperature of heat addition first of all. So earlier you were giving, let me use some color. Heat was added from point 2 to point 3. Okay, from temperature 2 to temperature 3. Let us say temperature 2 was 100 and temperature 3 was 500. For an example, what will be the mean of 100 and 500? 100 plus 500 is 600 divided by 2, that is your 300.
300.
Okay. But now the heat is being added after the regeneration from temperature A to temperature 3. So temperature A is higher than the temperature 2. So let us say temperature A is 200 and temperature 3 is 500 itself. So 200 plus 500 is 700 and mean of it will be 350. Okay, divided by 2. 700 divided by 2 is 350. Earlier your mean temperature of heat addition was 300. Now your mean temperature of heat addition has increased to 350. From 300 it has increased to 350. Okay, so eventually your mean temperature of heat addition rises. Mean temperature of heat addition rises. So I'll just close this table till clean the table till here. Mean temperature of heat addition increase. One point is this. Now, what will happen to the mean temperature of heat rejection? Earlier, our heat rejection was happening from 4 to 1. Let us say 4 was at 400 and 1 was at 100 or 50. So 400 plus 50, mean temperature of heat rejection will be 400 plus 50, that is 225. Now, after regeneration, rejection is happening from B to 1. B to 1. So let us say B is at 300 and 1 is at 50. And 300 plus 50, that is 350, that will be 175. Now your mean temperature of heat reduction has been decreased. All right. So mean temperature of heat reduction decreases. Mean temperature of heat reduction decreases. Other thing is heat rejection is also decreased because you were earlier giving the reduction from 0.4 to 0.1. Okay, so you needed an extra coolant to exchange the heat. Okay, but now you are using that exhaust heat to first go to the regenerator and using that exhaust to increase the temperature of the output of the compressor, and remaining from B to 1 you are using the coolant to the ambient or to the coolant to take out the heat for the heat rejection. So eventually your heat rejection has also reduced. Heat rejection is also reduced to cool down the fuel. So heat rejection decreased. And earlier you were, because of the regeneration process, your heat supplied has decreased, as we have seen here. Heat supplied has decreased. So eventually you are using less fuel to heat it. So that means your specific fuel consumption is also decreased. So the other terminology, the third terminology which I wrote here, the specific fuel consumption has also reduced. Specific SFC is also reduced. Okay. I hope this much it is clear, or any doubts. All these terminologies, that what are the benefits of using the regeneration. One way was this. Now let us see, we are using the regeneration, but there must be a effectiveness of that device, that is your regenerator. So let us calculate the effectiveness of the regenerator. Similarly, you will see in your heat and mass transfer subject, effectiveness of fins also. Okay, effectiveness of regenerator, or it is also called as thermal ratio. If the question it is asked what is the thermal ratio, it is same as effectiveness, or it is also called as degree of regeneration. Degree of regeneration. Just give me a second, please. Okay, so it is defined as the ratio of actual temperature rise to the maximum possible temperature rise in the regenerator, defined as ratio of actual temperature rise. So again, effectiveness will be either equal to 1 in ideal scenarios or less than 1. Temperature rise to the maximum possible temperature rise in regenerator. And generally the effectiveness varies from 70 to 80%. Generally, value of effectiveness varies from 70 to 80%. Okay. So what do we mean by this is, in physical sense, it means that by how much amount the exhaust temperature of the turbine was able to heat up the exhaust of the compressor or exit of the compressor T2. Okay. And whatever maximum it can give, that will be your effectiveness. Okay. So here when we wrote that here, then I wrote that this, if CP would have been same, then the effectiveness would have be here. Okay. So let us would have been near around 1, but it is not possible. So effectiveness is basically effectiveness epsilon is TA minus T2 to that of T4 minus T2. So actual rise was from 2 to A, that is TA minus T2 from 2 to A. And in ideal scenarios, your whole temperature can reach to whatever was the temperature of exhaust, it could have reached to 4. Okay, by the exit of the compressor. Okay, but which is not possible. So it is defined as the ratio of actual temperature rise from 2 to A to that of maximum possible temperature rise from 2 to 4. Okay. Yes. And in case of ideal regenerative cycle, effectiveness is always 1 or 100% in terms of that. Let me write it as a note. In case of ideal regenerative cycle, value of epsilon is 1 or 100%. So what do I mean by this is that my temperature of A could reach to temperature of 4 and temperature of B can reach to temperature of 2. Okay. Then only it will be an ideal scenario. And what will be the now we have got the effectiveness, we need to get the efficiency of this cycle also, because we have reduced the heat supplied, so efficiency is going to change, and which is eventually higher. So expression for that, let us get. So efficiency of simple regenerative cycle. Efficiency is net work, that of heat supplied, and net work is work done by turbine minus work done by compressor to that of heat supplied. So work done by turbine is from H3 minus H4. Work done by compressor was from H2 minus H1, and heat supplied is now from H3 minus HA, not H2. Okay, H3 minus HA. Okay. This is a simple regenerative cycle. But if I want to go in terms of a ideal regenerative cycle, where I'm saying that my heat interaction is the function of directly temperatures or enthalpies. Okay. So the heading will be like this: efficiency of ideal regenerator. So again, it will be efficiency is work net to that of heat supplied, and from first law of thermodynamics, net in a cyclic process, net work interaction is net heat interaction, Q net to that of Q supplied, and Q net is heat supplied minus heat rejected to that of heat supplied, and it can be written as 1 minus QR by Q supplied. Okay. And in terms of enthalpy, it can be written as 1 minus heat rejected is from HB minus H1, and heat is supplied from S3 minus HA. Okay. And in terms of temperature, if Cp is same, so it will be, because we are saying ideal scenario, so it will be TB minus T1 to that of T3 minus TA. Okay. And in ideal sense, when I'm saying ideal, that means effectiveness is 100%. That means TB will be equal to T2 and TA will be equal to T4 for ideal regeneration. So put that in the above expression. The efficiency ideal of a regeneration will be 1 minus TB is T2 minus T1 to that of T3 minus TA is T4. Okay. Let us take out T1 from numerator, T2 by T1 minus 1, and T3 from denominator 1 minus T4 by T3. And we know that T2 by T1 is Rp to the power of gamma minus 1 by gamma. And similarly, T4 by T3 is 1 by Rp to the power of 1 gamma minus 1 by gamma. So it is 1 minus T1 times Rp to the power of gamma minus 1 by gamma minus 1, that of T3 times 1 minus 1 by Rp to the power of gamma minus 1 by gamma. And on finally simplification, your ideal efficiency for a regenerative cycle will be 1 minus T1 by T3 into Rp power gamma minus 1 by gamma. This is your final expression. Okay, this is your final expression. Any doubts here? In getting the ideal efficiency for a regenerative cycle expression. Do you have any doubts? So if we see with the increase, how we can increase the efficiency. The efficiency is dependent on T1, T3, Rp, and gamma. Okay, on these 4 parameters. So efficiency will in efficiency of ideal regenerative. Should write here first the parameter. And here ideal efficiency of regenerative. If I'm saying my first parameter is temperature T1, if I increase the temperature T1, eventually my efficiency is going to decrease. If I increase the temperature T3, my efficiency is going to increase, because on increasing this expression decreases and it increases. Okay. Then other parameter is your pressure ratio. Again, if you increase your pressure ratio, your efficiency is going to decrease because it's in the numerator. And if you are increasing the gamma, that is the index, polytropic index for that gas, the efficiency again going to decrease. Okay, from this expression. So we can say that beyond certain pressure ratio, so we saw that only by increasing the temperature T3, the efficiency is going to decrease. The rest for other parameter increase, your efficiency is going to decrease. So there is one point to conclude here is that beyond certain pressure ratio, the use of regenerator becomes ineffective. Why? Because in that condition, compressor outlet temperature exceeds the turbine exhaust temperature. So you cannot increase the RP to whatever value. We saw that in the derivation where we were saying that RP, pressure ratio maximum, is square of RP optimum. But when you reach the maximum pressure ratio, the work net was 0 and eventually your efficiency will be 0. So you can eventually increase the pressure ratio to a certain limit. Otherwise, the temperature of the outlet of the compressor will be higher than the metallurgical temperature of the turbine. Okay. So what I can conclude here is that, on conclusion, beyond certain RP, pressure ratio RP, the use of regenerator becomes ineffective. Because in that condition, compressor outlet temperature exceeds turbine temperature. Exhaust temperature. Okay. So if we see from that graph also, which we had made earlier, where we had work net with that of pressure ratio, we had a graph like this. Okay. Where RP optimum was here and maximum was here. Okay. So at this point, there can be two possibilities, either here or here as well, for getting the work maximum. This is work maximum. Okay. But if we see, as work at the point 1 and 2 is same, work at point 1 and 2 is same, but the fuel supply is less for 1 than 2. So therefore we can say that we shouldn't increase the pressure ratio. Fuel supply for 1 is less than 2. Therefore, we shouldn't increase RP beyond the optimum value to get the work maximum. Okay. I hope this much is clear. Now, other way is reheating the gas turbine. So case 2 will be, I told the first case was decreasing the heat supplied. Other will be increasing the work turbine. So how you can increase the work turbine is by reheating in the gas turbine. Process of reheating. Case 2, reheating in gas turbine. Okay. So I'll join back in a minute, please. Let's wait. Meanwhile, you can think on this. If you have any doubts, you can ask. Okay, let's come to the next case. Case number 2, reheating the gas turbine. So by reheating, I mean is basically I'm doing the expansion of the working fluid in more than one stage. Okay, so I'm making two turbines to connect together. So one thing I missed here in the previous graph was that the turbines are being connected to a shaft. The same shaft. Yes. So reheating means expansion of working fluid takes place in more than one stage, and with help of reheating, that is, if I do the regeneration also, if I add regeneration also, network is going to increase more. So you can do the regeneration plus expansion of the fluid. Reheating, network output is increasing. So let us see the schematic diagram for it. So we had a compressor where the fuel entered, sorry, air entered, working fluid, and then the output of this, which got entered into the combustion chamber. Here the heat was applied first time, QS1. So from 1 to 2, then this was taken out, and finally it was passed through the turbine. Oops. See, and this is your turbine number 1, because I'll do the expansion one more time. This will be the output 4. This again, this setup is connected to a shaft. Okay. So this is your turbine number 1. Then the output is then further taken to the another combustion chamber. If you reheat once again, combustion chamber 2, this was combustion chamber 1. So again, heat was supplied. You can do reheating, you can do regeneration, depending whatever you want. T4, not T4, it should be just 4. So 4 and 4. And finally the out. So from turbine 1, it is not compressed again. It is just passed through the combustion chamber. That means at the same pressure. Okay. The pressure is going to remain same, but because of the combustion, the temperature is going to increase because of the heat supplied. And then it is passed through the next turbine, turbine number 2. T2, and this is 5, and finally output is 6. Again, this whole setup is connected through same shaft. Okay, same shaft. All right. So the net work is basically work done by turbine 1 plus 2 minus work done by compressor. So turbine work has increased, so net work output has also increased because you are expanding 2 times. You are getting 2 times the work output. Okay. So let us make the schematic diagram also for this. Sorry, the plot for also for this. So how the plot will look like. So this is temperature entropy plot. So from 1 to 2, the compression happened. 1 to 2 compression happened. Then 2 to 3, it passed through the combustion chamber 1 at constant. So pressure has been constant when it was passing through the combustion chamber. So let us say this pressure is, this temperature is T2. Okay. And at constant pressure, that is P2 equal to P3. Okay. Then it was expanded through the first turbine, that is 4. Okay. And then it was again reheated at the constant pressure. So eventually it would have gone straight, but it has again increased, and let us say the temperature rise to some temperature 5. Okay, and the pressure was again remain constant. So that is P4 equal to P5. Okay, P4 is equal to P5. Again, write in some another color. P4 equal to P5, and let us say it is intermediate pressure, PI. Let us say it is PI, intermediate. Okay, and let us say this was PH, higher pressure, because after the compression, the pressure was increased. And finally, it was expanded once again, let us say till 6. And T3 and T5 are not same. I'm not making them same. Don't think that is why I'm writing with the marking with the points, and neither T4 and T6. And finally, it was rejected. Okay, it was rejected. Okay. So eventually, it should have, if there was no expansion, it would have gone from 3 to 4 directly, 3 to 4 dash directly. But now it has gone from 3 to 4, again expanded from 4 to 5, and again a work output was produced. Okay. And let us say this temperature is higher than T2. Okay, T6 is higher than T2. And again, finally, the pressure here will be same, P1, P6, and P4 dash. Right here, P1 is equal to P6, and if 4 dash would have been also there, so it would have been same, P4 dash. Okay, so let us compare again the table from the without expansion or reheating compared to with reheating. Okay, so 1, 2, 3, 4 dash and 1 would have been without reheating. 1, 2, 3, 4 dash and 1. Okay, without. And in actually with reheating, the cycle is 1, 2, 3, 4, 5, 6, and 1. So earlier, work by the compressor was H2 minus H1. But here the work done by the compressor will also be same because only one compressor is used. Then work done by the turbine would have been S3 minus H4 dash. But now expansion has happened 2 times, so work done by turbine is increased. So that is S3 minus H4 plus H5 minus H6. So eventually your net work has been increased. Third, if net work is work done by turbine minus work by compressor, so here net work will be work done by turbine minus work by compressor, cause work done by turbine has increased, so net work has been increased. Now heat supplied, fourth, Q supplied was earlier S3 minus H2, but this time 2 times a reheating has been done. So 2 combustion chambers are there. So one is from S3 minus H2 plus H5 minus H4 also. Okay. So one heating is from this to this and another is from 4 to 5. 2 to 3 and 4 to 5. Okay. So again, net heat supplied has been increased. Okay. So we can write that for those 4 special terms. Again, we can say that mean temperature of heat addition has been increased. Earlier, the mean temperature was from this to this. Now it is from this to this plus this to this also. So if you mean for all the 4, divide by 4, it will be a higher value. Okay, so mean temperature of heat addition has increased. Then mean temperature of heat rejection has also increased. Why? Earlier the rejection was from only 4 to 1, but now rejection is from 4 to, sorry, rejection is from 6 to 1. Okay, rejection is from 6 to 1. So temperature has risen if you take the mean. Okay, so mean temperature of heat rejection has also been increased. Next thing, heat rejection, mean temperature has increased, so heat rejected has also increased. Because earlier it was from 4 dash to 1, now it is from 6 to 1. And heat supplied has also increased because you are providing by 2 combustion chambers. So heat supplied has also increased. We have seen the heat supplied has increased. So if heat supplied has increased, that eventually means that efficiency is nothing but work net by heat supplied. Okay. So there is a possibility when heat supply is much higher compared to the network output, the efficiency could have decreased at that point of time. The heat supplied is much higher compared to the network increase. So this is a possibility. And mean pressure ratio is also decreased. So earlier the pressure ratio was from 3 to 4 dash. If I say the pressure reduction was from 3 to 4 dash, but now the pressure reduction is from 3 to 4 and then 5 to 6. So pressure ratio reduction has been, mean pressure ratio has been also decreased. Okay. I hope this is clear. And similarly, when we had a condition for maximum work output for a Brayton cycle, here again we can have a condition for maximum work output for a perfect reheating as well. Okay. So let me derive that as well. Just give me a second, please. Condition for maximum work output for perfect reheating. And what do I mean by perfect reheating is basically whatever was the temperature rise from 2 to 3 till this value, same the temperature rise from 4 to 5 is also same. Okay, so both T3 and T5 must be same. But it is not that T3 and T5 can be greater than the metallurgical temperature of the blades of the turbine. You cannot increase the pressure ratio in such a way from the compressor or by the heating from the combustion chamber that it reaches the maximum temperature of the metallurgical limits of the. Okay, you have to be in under the limits from the metallurgical limits of the material of the blade. Okay, so let me make again plot temperature entropy. The cycle will now look like this. One, two, three, four, five, and 6. And I mean to say that T3 is equal to T5. Okay, 1, 2, 3, 4, 5. Okay, and this is nothing but equal to T maximum. So work net is nothing but work turbine minus work by compressor, and work by turbine is work by turbine 1 plus work by turbine 2, which is equal to H3 minus H4 plus H5 minus H6 from 3 to 4 and 5 to 6. Okay. So you can take in terms of temperature Cp T3 minus T4 plus Cp times T5 minus T6. Okay. If I take T3 from the first one, it will be 1 minus T4 by T3 plus Cp times T5 from the second one, 1 minus T6 by T5. Okay. Let us say this is equation number 1. We know that T4 by T3 is P4 by P3 to the power of gamma minus 1 by gamma. Let us say this term is basically x. Okay. Gamma minus 1 by gamma. So P4 is nothing but, if you see, let me write, let's say here, P4 was P intermediate and the P3 was P higher. Okay. P higher. So I'll write here P4 is intermediate and P3 was P higher with power of x. Similarly, T6 by T5 is, let us say this is P lower L. Okay, P lower. So T6 by T5 is P lower by P intermediate to the power of x. And let us say this is equation number 2. Now use this equation 2 in 1. Use 2 in equation 1. Put these values in terms of I and H and L. So work done by the turbine will come out to be Cp times T3 2 minus Pi by P higher to the power of x minus P lower to Pi to the power of x. Okay. And for perfect reheating, we are saying that T3 is equal to T5. T3 is equal to T5 for perfect reheating. Okay. So if you want to find out maximum of any value, you need to differentiate it. And what is the variable here? T3 is constant, P lower is a constant value, P higher is a constant value. Only the variable value is P intermediate. P intermediate can change. So P intermediate can only change. So you differentiate with respect to P intermediate. So for maximum work output, work turbine, D of work turbine by D of P intermediate, you differentiate it, you will finally get that this expression minus x times Pi by Ph, it is power x, it is power x minus 1. Okay. Plus P lower to the power of x, x by Pi power x plus 1, and it will be equal to 0. So differentiation should be equal to 0 for getting out the maximum value. So from here, on simplification, you will get Pi to the power of 2x is equal to P lower P higher to the power of x. And from here, your P intermediate will come out to be P lower into P higher. This is a condition for maximum work. So the condition is that intermediate pressure should be square root of P lower times P higher. Okay. Let us say this is a condition A. Okay. Let us say this is a condition A. Now put this condition A in your equation number 1, back in equation number 1. This is your equation number 1. Here you had the work turbine, because eventually we need to get the work turbine. Okay. So putting A in 1, you will get the work by turbine is Cp times T3 1 minus under root of P higher P lower by P lower to the power of x plus Cp times T5 1 minus P lower by under root of P higher P lower to the power of x. Okay. So on simplification, you can write Cp times T3 1 minus under root of P higher by P lower. Sorry, P higher by P lower or P lower by P higher. Sorry, yeah, I was writing wrong. P lower by P higher to the power of x plus Cp times T5 1 minus under root of P lower by P higher to the power of x. And this is same, so it can be written 2 times. And T3 is equal to T5. So 2 times Cp T3 into 1 minus under root of P lower by P higher to the power of x is your work done by turbine. Since T3 equal to T5. Okay. For perfect reheating. All right. So work done by the turbine 1 is equal to work done by turbine 2. All right. So this implies work done by turbine 1 is equal to work done by turbine 2, because both expressions are same only. Okay, both expressions are same. That is why we have written 2 times and both are equal. So finally we come up to the conclusion that note condition for perfect reheating with maximum work output. Condition for reheating with maximum work output. So what will be the condition? First condition was that T3 should be equal to T5. Second condition which we derived was intermediate pressure was under root of PL times pH. Third condition we have got is that work done by turbine 1 is equal to work done by turbine 2. And one more condition is that T4 will also be equal to T6. This one. This will also come out to be equal. All right. We can derive this, but I don't want to go into the T4 equal to T6. Another point I want to write here is that in the note, we can provide the regeneration also. The scope of regeneration increases the use of reheating, because again the turbine exhaust from both the turbines can be used again. Okay. So I can write the point here. The scope of regeneration increase with use of reheating, because turbine exhaust temperature increases. That is T6 is greater than T4 dash. Okay. So your heat supplied will decrease eventually. Okay. When you do the regeneration. Okay. Any doubts? Anyone has? Please ask. Santosh, do you have any doubts?
No, sir, I don't have any doubt.
Okay, great. Now the case 3 will be that you decrease the work of the compressor to increase the efficiency. And what we can do the intercooling. And I will discuss this intercooling process in the upcoming tutorial, and we will also do a one very good question related to this. Okay, where I will involve everything, all the three cases. So maybe we can end this tutorial here itself today. Okay, I don't want to, because if I start, then it will be taking more time to complete. Okay, so I hope that everyone is regular to the lecture videos by the professor on the NPTEL portal, as well as you are watching regular to the tutorial videos. If you are not, because the NPTEL team provides you with the Google Sheet where you see the links for each recording session. So, as well as the PDF of the notes are also uploaded on the Google Drive link, which is also shared simultaneously. But if you are new, you can directly check through my YouTube channel where all these recordings are uploaded. And the name of the YouTube channel is NPTEL with Varnit. So for the corresponding playlist, you will see the week-wise corresponding playlist for this course, IC Engine and Gas Turbine. You will see week-wise tutorial videos, and in each video description, you can see the Google Drive link which will redirect you to the PDF notes of the sessions. Okay, so maybe we can end the session if you have no doubts. Thank you so much.